we're going to do a new example. And let me show you how we're going to approach it this time. So this is another example of the Fundamental Theorem of Calculus. Okay. So I'm going to give you a function, and the function is f of x is equal to 0.5 times x minus 7 times x minus 3 times x minus 2. Okay. And I've got the picture of what that graph looks like right there. This is the graph of this. Okay. So let's demonstrate what's going on here. Draw yourself a sketch. Okay, so just draw yourself a sketch of this. So it does this, then it does this, and then it does this. And this is f of x. Now, I've chosen 2 points on the graph, and the 2 points that I've selected are f of 1 is equal to 4, and f of 7 is equal to 10. So I'm going to just plot those here. So this one here, this is 1 comma 4. And over here somewhere is 7 comma 10. So this is where 1 is, and this is where 7 is. Okay. Now, by using the Fundamental Theorem of Calculus, I'm going to ask you this. What do you think the answer is What is the answer to this question? Don't say it out loud. Let everybody think about it. Notice that this does say f prime of x. You can look back at yesterday's notes. What we've done over the last 2 days, we've been trying to explain what this whole integral thing means. Okay, does anybody have an answer based upon what you see here as to what you think the answer is to that? Gunnar? 6. Did anybody else think 6? If you are thinking 6, you are correct. Okay. Gunnar, can you explain what this thing means? Good. It's the net change. So let's say it here. The net change in f of x on the interval from 1 to 7 is 6. We know it goes up. We know it goes down. We know it goes up again. But when all is said and done, it went up 6 units. Okay? It was at 4, and it ended up at 10. It went up a total of 6. That was the net change. Okay? All right. We're going to prove this now using the calculator. Okay? So grab your calculator and type in this function for y1. Okay? Now, with the function in there, don't graph it. Okay? So take your equals off, take the equals so that it's not highlighted. Okay? We're not going to graph that. We're going to graph its derivative. Okay? So, to graph the derivative, we're going to press the math key, go down to number 9, which is your FNINT. And if you have the new operating system, it looks like this. So we get to type it in exactly the way we see it here. If you don't have the new operating system, I'm going to write up there what it's supposed to look like. Oh, my bad. We're doing the derivative, not the integral. Sorry. No one said anything. Math. We're graphing the derivative. So the derivative with respect to x of y1 and evaluating it at all x's. If you've got the an 83 or the older system, you're typing in nderive y1 comma x comma x. Okay, do a zoom 6. It's numerically calculating each of those. Okay. I've got the derivative and the function on the same one here. So the f prime of x is the red one. Okay? Let's see if this kind of makes sense. The derivative is positive here until it gets to here. This is where a critical number is. Then the derivative is negative all the way to here. That's where another critical number is because f prime is equal to 0. And then the derivative becomes positive. So this function should be increasing, reach a maximum, decreasing, reach a minimum, and then increasing. This matches perfectly with the actual function of what it does, because this one is f of x. Make sense? So, the fundamental theorem of calculus says, now we're going to integrate on y2. Okay? So, hit the second calc button. And then now we're going to go down to number 7. Now this is really important. Okay, because we took off the other one. If you don't have the right function up there, you're going to get it wrong. And if you happen to be graphing both of them, then y1 pops up first. So we have to make sure that we're working off of y2. The lower limit is 1. The upper limit is 7. And it goes ahead and does its shading thing. And it tells us the answer is 6 point something. This is a round off error on the calculator's part, but the real answer is exactly 6. Okay. So the answer to this integral is equal to 6. It comes from the fact that the area bounded by the derivative and the x-axis is has a total area when we can include the positive areas and the negative areas. The total area of that ends up being exactly 6, because that's what f of 10 minus f of 7 minus f of 1 is equal to. Yes? Oh, thanks. Does not look like this? Now, on my graph, this brings up the awesome point of this is an antiderivative. Okay, my function here, we both have the same derivative. Okay, so watch this. Every one of these has a different c value. But do you notice the change in between f of 1 and f of 7 is exactly the same? Okay? Yes?
So why don't we just, why aren't we just, just do f?
Because what we're going to ultimately do is, given a derivative, we're going to find exactly which function it is by knowing a specific point on the graph. And that will allow us to find what the constant is. So that's what's going on here. All right, watch this. This is on my little thingy here. Let me show you this. If I include all of these, it shows the area here, okay? And what I can do is I can go left and right, and it will shade or unshade, okay, wherever we want, okay? And we can figure it out, okay? All right, now. This one I generated, I told you what it was. What I want to do right now is I want you to just make up a function. Okay? We'll do it as a class first. I don't care. If somebody think of a function, we'll take whatever you got and we're going to prove this thing works using this. So it can be as crazy as you want to. Just has to be continuous and differentiable or integrable on the interval. X plus 1 is a good start. Let's make it a crazy one. I don't care. To the 16th power. Want to add anything else to this? Now, I'm going to stay away from the cotangent or the tangent because there's places where it's undefined. And that can mess it up. So we're going to keep them continuous. The sine of e squared. That's a constant. Okay. The sine of e to the x. Okay. That's good. plus 7x?
Yeah, sure.
Okay. Okay. That's pretty crazy. I think that's that. Now, I want an interval. I want an interval.
0 to 10.
Any can do decimals. 7.65 to 13.2. I'll take it. Okay. Now, what this means is for this wacky function, we're going to find the net change between x equals this and x equals this. Okay? And then we're going to prove it on our calculators. So here we go. The integral from 7.65 to 13.2 of f prime of x dx equals. Now I'm going to show you something really cool. You don't have to use your calculator in the graphing form to do this. Okay? Watch this. At this, have a clear screen. I want you to find, press the math key and go down to FNINT. That's our function integrator. And we can just plug all of them in and it'll tell us what the answer is. So 7.65, 13.2. And then you got to type the function in here. So do that very carefully. And then we have x. And what I have to tell is the people who don't have this, this is what you're going to type. You have to type FNINT. Then the first function, the first parameter is the function. And it's the derivative of the function. So that's what we got to watch out for. This, you know what we should do is we should probably use y1 and y2, don't you think? Yeah. Put that function into y1. Find the derivative of y2 because you've got to take the derivative of that first. So the first parameter, if you have the old operating system, you go f prime first. Then you do x. Then you do 7.65. Then you do 13.2. And those are the four parameters. There's four things separated by 3 commas. Okay. Here's what I'm going to do. I'm going to go to my y equals, and I'm going to replace that one that we had in there. And so, x plus 1. Yeah, we can do it. Like I'm going to do it right here, and then I'm going to use y2 sine. Okay. My f of x is in y1. The derivative of f of x is y2. So when I do this, I'm going to put in y2 here. And it's going to know what to do. I don't remember.
So we have integer, we have fraction, we have earned, then we have however, integrate those to nothing.
All right. We're going to have to do a little resizing here. Oh, 2.73 times 10 to the 18th. Okay. Now, here's how you can actually check this. If I say, watch this, if I take 7.65 and actually we don't even need to do this. We can go right to the table. If you go to your table and you type in 7.65 in for one of them, and then you type in 13.2 for the other one, then, well, we don't have very much accuracy, but the difference between 3.1 times 10 to the 18th and 1.8 to the 15th is just about 2.0 times e to the third. Okay. All right, tomorrow make sure you have your orange packet here. We're going to talk about applications of this tomorrow. This is the net change in the function. Oh, let's look at that, the wrong one.